All right, slowly but surely getting back into the class.
Yeah, that was a good matchup. That's a Super Bowl matchup for you. He's still a good pick. No, he's always so.
There we go. Okay. Thanks for being here, giving the 5 minutes. Gotta turn that off. There we go. 5 minutes grace period. There's a meeting, big faculty meeting with the new dean. So like big deal, but yeah. But I was late. I had to leave early and be late, so I lost out on everything. But here we are. We made it. Another week down. It's Friday afternoon, end of week 2. Pretty sweet. And last time we kind of like jumped a little bit out of order from homework 1, went right into, because the question came up like, when you say solve for x of t, what are you talking about? And we looked at kind of a reminder, like if you can set up a free body diagram where acceleration is constant, then those kinematic equations give you position, like it's telling you the geometry of motion. And then we did another review from a whole different course of calculus of like how do you integrate, if I know dv dt equals v, how do I get v as a function of time and all of that. And now we've got a whole nother problem in part C where we have a spring. And what does that differential equation look like whenever we have a spring acting on a mass? Do you know what is MA equal to in that case? Yeah, let's do this one. What does MA equal to? Yeah. Negative kx? What do we think? Seems right? Negative kx? Why not positive kx? Yeah.
The spring force goes in the opposite direction of motion. It's like the restoring force.
Yeah, so it's always like restoring. So if we push the thing to the left, like if we have a negative displacement, then we do have a positive force, but now it's a negative, positive, k, negative. Yeah, anyway, positive kx for that negative x, negative k. Cool. Okay, so we have an equation. Let's get it into another thing. D squared x dt squared equals negative k over m times x. Have you seen an equation like this before? Maybe? I mean, if you're like reading like popular physics, like in your spare time, then it's like, of course, it's a simple harmonic oscillator equation. But if you're not, if you're like just kind of hanging out, like, yeah, not absorbing physics at all times, then this might not pop out as, yes, the SHO, the simple harmonic oscillator. Do you know how to solve this differential equation? Yeah.
I kind of remember us do something with cosine and sine.
Ooh,
Because
cosine sine. Yep.
when you differentiate it twice, it goes back to the same thing.
Yeah.
Because you have the x and acceleration.
Yeah, and this is like something that a lot of people, it's something that is hard to kind of deal with in dynamics. Is like when we write the letter x, like that variable, it's not like there's one value. This is like a function of time. Like it had, for every point in time, there's a different x. And so its derivative, for every point in time, it has a different second derivative. Like they're all just these like continuous functions over time. So one way to think about this is like the only function that if I take two derivatives of it, it gives me the same function back. Well, one would be 0, but 0 is, that's boring. Who wants a 0 function? And then the other one would be like a sine function or a cosine function. So that's one way to think about it. That one's a nice way to go about it. Have you tried other ways? Maybe not. Is anyone taking differential equations right now? Yes? Some. I think right now it's all first order differential equations, right? Well, you're going to jump right ahead into second order because it's just doing the same thing twice, right? So I think in differential equations, do you give it a like an integrating factor, like this? Have you done that where you say x is no? How do you solve first order? Oh, change my color. How do you solve the first order ODEs? Like how do you do that? Do you just directly integrate it? Yeah.
We just do like integrals on both sides.
Okay, integrate both sides. Is that, and that's where you're at so far? Okay. Turn into like separable integral. Yeah. Okay, that works. One shortcut for this, and this is kind of nice, is that I already know that the only way to get a derivative to equal itself is some kind of exponential function. Like I can go through and do the integral, get log of y, and then e to the log is now y, and then log e to the something else. But I could just say, well, y of t has to be e to the est. I don't know what a is, I don't know what s is, but I know it's got to be in that form, kind of that way. So if I plug that into this equation, this becomes as e to the st, and this becomes 2a e to the st. On both sides I have a, and on both sides I have e to the st. So s equals 2. So now I know a bunch of, I'm using all these arrows. They're magic arrows because there's magic happening as we move along. Magic. So now I know y is a, and again, I still don't know what a is, but I know that there's a constant, e to the 2t, because I just solved for the only way that for that equation to work out, so it has to have that 2 in that s part component there. Kind of makes sense. This is like the quick way if you don't want to go through all the integrals and stuff. Stick to derivatives. Plug in an equation that you know should work and then take derivatives of it rather than taking integrals. Integrals are always hard. You should be able to do everything with the derivative. for the most part. That's what like Richard Feynman did. He never did integrals. He just did derivatives and then solved for what the integral would be if you knew the derivative. All right, so what if we do the same thing here? Try that. What would x of t look like? What is x of t in that case? What do you think that one would look like? Still e for st? Not sure. Something different. What does that x of t look like? No idea? Well, it's just random guess. E to the st? Yeah, we can do that. Sine of something over 2. Sine of t over 2. Okay. I'm just peeking at what people are working on too. Sorry? One way to do it is like, we know that only way to get derivative equal itself is e to the something. And then s would end up being like some kind of complex number. Yeah.
A cosine st.
Yep. Yeah, we could try a cosine st like that. I'm gonna use a new thing, like omega, just because omega is a good like frequency designator. So let's try it out. What's second? Well, here, I know the right-hand side, right? Negative k over m times a times cosine omega t. What's the second derivative of a cosine omega t? If I take two derivatives of a cosine omega t. Negative cosine? Yep. Yeah. Negative cosine omega t. Anything else? I guess I do need that a, right? Because that didn't go away. And then negative. And then omega squared. Yeah. Yep. Cool. Seems like it worked, right? Because I can take this, take that, cross those out, and now I have omega squared is k over m. Seems like it worked. How much room do I have? So the part that I didn't get to was plugging in the initial conditions. All right, so let's say, again, plug in here, magic arrow there, and now we've got x of t is a times cosine root k over m times t. X of 0 is 0, and that's going to be a cosine root k over m times t. V of 0. So velocity has to be that derivative of x of t. So then this would be, sorry about that, 10, which is a times root k over m. Oh yeah, negative times that sine root k over m times t. Can I satisfy both of these initial conditions? And really this is t is 0, right? So times 0. What do we think? Can you pick an A so that at times 0 it equals 10, and then it also equals 0? What would A be? Because it's cosine of 0. 1. So A, what's an A? AN is 0. But then what's sine 0? 0. So we end up with like x of t is 0 for all time. And that sounds boring. X of t is 0. And just throw your hands up. Mic drop. 0. What do you think? How do we? Let's come back up here. When we first said, let's find that solution, like what is the second derivative such that it's equal to some constant times itself, we picked cosine. What if we had picked sine? What would it change? Like this equation would still be sine and sine, right? If I plug in x of t is a sine omega t. So both of them are just as good of a solution. So instead of just saying that it's cosine, let's give it two unknown, and A and B are now called like integration constants that we only know them once we plug them in and figure out like for those initial conditions. And we still get the same result that omega squared is still k over m. It's just now we also have b sine k over m times 0 and b root k over m cosine so we get those two extra integration constants. Roughly this should kind of thinking about the last problem that we did where we did the integration once and we plugged in initial velocity. We did the integration again, then there's a spot for initial position. Same thing here. There should be two constants because we need two integrals to get to a solution of x of t. So if we have second order differential equation, we're going to end up with two integration constants somewhere spattered in there somehow. This is a quick like crash course on differential equations, and I'm like skipping over a lot of like the power series and calculus and stuff. This is just what we need to know to solve differential equations. So there's lots of other cool stuff that you can learn about ODEs, but we don't need to know any of that for this. All we need to know is that d squared x dt squared equals negative omega squared x is always a cosine plus a sine. And for the most part, we're only going to deal with either harmonic oscillators or like damping and damping is separate from spring forces. So we don't have to deal with power series and all that, proofs of these things. But anyway, now, keeps trying to pop that up. Now try to tell. what is A and what is B? We figured out the first round that A had to be 0. So what is B so that we can get both initial, we have initial position is 0, but initial velocity is 10. What are those? Yeah. Nice. So this one's 0, and this one's 10 over square root, so 10 root m over k. Over, yeah. Cool. So then we have our answer, right? X of t is not just cosine, but it's 0 cosine plus 10 root m over k. Oh wait, we don't even need that. All we need is that. Yeah, sorry. Root m over k times sine omega t. And it satisfies our initial conditions because sine of 0 is 0, which is what we want. And then take a derivative, cosine omega is going to give us that 10 meter per second initial speed. Nice. All right, so now we've got like xc, we have xb, we have xa, we have all these different solutions for x, like x of t has been solved for. How do you, if you make plots, how do you like make a plot? The most popular, like the most used engineering software is Excel and like Google. I guess we don't have Google Sheets anymore, so we would be using like Excel. But how do you prefer to make plots? If you're gonna compare answers, like I have these functions, what do they look like? I like either MATLAB or Python or any of those. It's just like I can plug in the formulas. It just makes more sense to me. I used to use Maple years ago, like another. Let's write down, let's like collect everything we have here so far. XA is negative, or wait, 10t minus mu g t squared over 2. XB was this one, V0m. So I have like 3 different x values. Do you want to do it in like Excel style? If we're making like a plot of stuff, what do you want to do? Excel? Python? MATLAB? I'll do anything. C, I would have a little more trouble with compiling it, but if we want to do it, I can figure it out. MATLAB, Excel. All right, we can do Excel. Oh, I should be signed in, right? All right, we'll make a blank spreadsheet. Zoom in. Time in seconds, XA, XB, XC. So no matter what I want to do, oh my god, way too many options. No matter what I want to do, time is an independent variable. Like whatever XA does, it's a function of time. It's never the opposite, unless we get to relativity. Then time is also a function of velocity, but we don't have to worry about that because time and space are constants in our little Newtonian physics world. So I'll set up 0, and then this is going to be 0 plus whatever my time step is. Say like 0, let's do 0.1 just so I don't have too many. What? Oh yeah, should be A2. Oh my god. And then we're going 0 to 3 seconds, I think. So I don't need any of those. XA, I can use time as part of, so it's going to be 10 times time minus mu, I think was 0.5, 9.81 over 2 times t squared. Sure. Autofill. And I think I did this right. It doesn't look right. No, it's okay. And now this one's going to be V0 10 times 1 kilogram over B. Is it 1? Thanks. Over 1 times 1 minus, I think it's EXP. Yeah, EXP of -1 times time. Sure, autofill. Then finally, we've got 10 times square root of 1 over 10 or 5? What is 4? So we got 4 Newton. So 4 over 1 times the sine of, I'm going to take square root of 4, so 2 times time. And now I've got like one column. First column is my independent variable. Then I've got solution A, solution B, solution C. Making progress. And this is the part that drives me crazy, but we're going to insert a chart. We don't want column, we want a scatter plot. I gotta make it bigger so I can see everything. Oh, that was B. Oh my god. What? Why won't it let me? A2 through A32. Alright, there we go. C2 through C32. Then add another one. D2 through D32. Okay, so I don't have like labels on things, but what do we think? Which parts are what? C is yellow? Yeah. This one, amplitude looks big. I wonder. I think this should be 1/4, right? There we go. That looks better to me, at least from just seeing it before. The amplitude was 1/, that natural frequency. Which one, what do we think, blue versus red? What are those two? Blue is B. Blue is B. Maybe. So red is constant acceleration. Other way? Where? Yeah, this one has, like, the faster I move, the more force there is. So the slower I'm going, the less acceleration I have. How the slope is kind of changing. It's not, and if you're not seeing that, it's not that it's like, oh, you should know this by now. It's more of like you're looking at an Excel plot that they're not very good at visualizing stuff in general. But it's fine. We got something. The one thing that we do know that kind of does stand out to me is that these blue dots do look like a parabola. Like it looks like a constant acceleration kind of line to me, versus that red line where maybe if you squint and look at a small enough part, maybe it is a parabola, but it seems like something else. There's some other change going on there. Are we done? Have we plotted these and it looks like friction, damping, and springs? Does everything look good? Does anybody see a problem with? You do? Okay. Yeah, one of these should be constant, right? So here, I'll make bigger time steps. So now I'm looking at double the time. I increase like less time steps, but bigger. So now I'm looking at more time, but same amount of data. So spring is kind of doing exactly what we would expect. We're not damping it. There's no friction. It's just going to keep bouncing back and forth until some kind of external force tells it stop. Now we have red line, where our viscous damper, we got to some point and it's just for the most part, it stopped moving. Like, it reached a zero velocity for all intents and purposes. What about friction? What did friction do? Yeah. It started pushing it. I mean, it's acting in the same direction, right? But it kept pushing it back. This one is a little, I mean, can I push this chair and expect it to come back to me? I mean, there it's like hitting stuff. But can I expect it ever to come back? Why? What's with friction that's different that we did not capture so far? If there's no motion, there's no friction. So friction is always like, it's a weird force because you need some, if you want like drag, like friction to be removing energy, it has to be moving. If something comes to a stop, there is no force of friction anymore. It's gone. There might be some kind of static friction, like if it's on an incline or something, but it's a force that's only there when things are in motion or something's opposing it. So since we're in Excel, we can look at all the data this way. And one way to do this, again, it's not like the best way, but one way to do it is scrolling through and figuring out like what was the max displacement that I got to. And up here it's like 7, down here it's something like 7, and it gets to 9, gets back to 9. Right around here, it got to 10.2 and then started moving backwards, like started moving back to 0. So what I could do is say that this is 10.2 and copy it down. So that now when I reach that maximum point, it stays at that max. It doesn't, when the velocity got to 0. A better way is solving for, like, take a derivative. When does velocity equal 0? At time equals something. Here, probably around 2 seconds. I think it's like 1.9 something seconds. And then whatever position that was, just have a constant position that way. This is more the numerical way. Just find the max and then keep the max constant. Now it looks better, right? Friction comes to a stop, damping comes to a stop, and then if there's no friction, no damping, it's always moving. Cool. And how do I series? I want to name them. Ugh. Anyway, I'll let you figure out how to name them, because I think I would have to go in. I always forget. I use Excel so rarely now, but there is a way. You could change the label up above. But in terms of where this all came from was, oh my god, starting off with like, what is x of t? Like, how do we get there? And then the second part is, when you plot it, what is the plot that we're looking for? And here, 0 to 3 seconds, so we get a sense of like friction. If you don't have some kind of cutoff of like when it stops moving, friction's gone, then then the solution is just a constant acceleration problem. And then also just seeing like some oscillation and some damping, but comparing those different types of forces. Cool. Now one, that was a little more of a demo today. Usually I like to have you do it and help out, but sometimes it helps to just see how one way of doing things. Should we keep? I guess we didn't get back to this question about the bobsledder. Yeah.
Asked a question before. He wants to do that sale and plot stuff on the end.
Yeah, so if you like Excel, then that's great. Like you can plot an Excel plot. I've seen people do it by hand, but I haven't seen anybody like accurately do it by hand. Because like people used to draw plots by hand, but they're like plugging in numbers and using graphing paper. So I mean that's if you prefer that, then go for it. But I feel like that's a lot more work than Excel or MATLAB, Python. Like somehow just getting a plot that way. Yeah. Yeah.
Why are they all moving infinitely?
Why are they all moving infinitely?
Yeah, like in the graph, like why do you top it off and have it like keep moving this way? Because like wouldn't it actually like go down to 0?
No, because this is position. The velocity goes to 0,
Yeah, that makes sense.
but position like hits some maximum spot
Yeah.
for at least for like damping and friction. For springs, it's different because there we have like kind of this idealized system where.
But I was thinking of it like velocity.
Yeah, but as velocity, you would see it like some initial velocity and then go down. Yeah, do we want to put? Oh. What? This should all be 0 velocity, right? E12 minus, oh, E, what? No. So here, like for friction, start off at 10 meters per second, times 0, and then it drops, constant speed change, and then 0. And there I'm doing like a numerical, like neighboring points of position divided by change in time. Cool. Thanks. Today was like demo day. We'll do more like hands-on stuff next time. Have a great weekend.